My name's Carl Whitfield. I'm a postdoctoral fellow at the University of Manchester, and I'm going to just go into a bit more detail on some mathematical modelling aspects in respiratory medicine. In particular, I'm going to talk about models of breathing in order to show a few examples to give you an idea of what the kind of models that we're talking about. So a little bit of background to start with. Just so we're all on the same page, I just wanted to give a quick clarification of what I mean when we're talking about modeling and models. So a model is some simplified representation of some aspect of reality. And we use models all the time. So for example, if you try to catch a ball, you sort of build a model in your head of the trajectory of the ball and move your hands accordingly to catch it. All of that, of course, happens subconsciously. Models don't have to be mathematical in nature. This is an example of a physical lung model built at the University of Nottingham that simulates breathing. And mathematical models essentially can take us from data and assumptions through to predictions and interpretation. So an example might be predicting the path of a hurricane, which is all well and good until someone draws on your results. So and we're focusing here, I guess, more on biophysical models. That's in our name. And as Bindi mentioned, this is using and incorporating the sort of physical properties of the biological system, and they're incorporating knowledge into the models that mean they're constrained more closely to reality. The challenge in the lung is that it's very structurally complex. So we can see here a resin cast of the airways and the vasculature of the lungs, and see that it's, there's many airways. It's very complex. And here from a micrograph of the alveolar air spaces, you can see that there's essentially a huge amount of detail that we could incorporate into models. And of course, some aspects can be understood by simple analogy. So for example, a basic model of breathing might just connect tubes to bags to represent the airways and the alveoli and simulate the flow of gas. But the model used very much depends on the question being asked. So here's an example of a more complicated model looking at the transfer of gas, transfer of gases from the airways through to the bloodstream. One case study that I wanted to focus on in a little more detail, where modeling has had a lot of input over the years, is in inert gas washout. So this is a lung function test where a low concentration inert tracer gas is breathed in and out, and the resulting signal is used to assess lung function. Mathematical modeling, particularly seeing papers in the 80s and 90s by Paver, Engel, Verbank and their groups, led to the development of multiple new indices for interpreting this data and trying to unpick whether the patchiness that maybe was seen in someone's ventilation was coming from the airways, or whether it was coming from deep within the lung. So these indices are still often used in studies today, but they can be affected by confounding factors like varying breath rates and breath sizes, which can be hard to account for. So where are we now? Well, we have ubiquitous and abundant computing power, even in clinics and even in our pockets. And we also have the development of new statistical methods, AI, machine learning techniques, things that allow us to connect data with models more effectively and more efficiently. And on top of that, we have decades of physiological research. That means we can do things like build airway network models based on images, as you can see in this video here. But also, as Bindi mentioned, we have new technologies, and I'm just going to mention the same two again, actually. So hyperpolarized gas imaging, for example, allows us to see exactly where in the lung the gas is reaching. This is an example from the Polaris imaging group in Sheffield. And there's also technologies to allow us to analyze the gas content of people's breath in real time. And these can be used as biomarkers for various conditions, and to monitor various things that might be contained in people's bloodstreams and metabolism. But these multiple data points can be difficult to understand in a holistic way, and that's where biophysical modeling can help to try and connect together these different dots. So to finish up, I'm going to highlight a few cases, by no means an exhaustive list, of where modeling is shown to be useful in these sort of areas and connecting up these data sets. But first, I was just going to take a step back and ask, are we keeping up with the cardiologists? So cardiology is often held up as an area where biomechanical models are used a bit more in clinical practice, or at least in the development of treatments. And here's just a couple of examples. So here's an implant, for example, or patent for an implant, I should say, that includes a biomechanical model to accurately measure the heart function. And another example from the same group, the Edelman group, is fluid mechanical modeling of stents in the arteries, and therefore optimizing stent design for deployment in the arteries using computational fluid dynamics. And again, as Bindi mentions, there's examples where in respiratory medicine we've been able to combine knowledge across scales to build models, more realistic models of the lung, and incorporate bits of information that we know about from down from the smallest of scales up to the whole organ scale. So on the left is an example of a Asner mechanical model. So this is the very tiny scale sort of structure of the alveoli and how they're connected. Building mechanical model of that, and then incorporating that into a whole lung model with the airways and everything interacting and pressing against one another to get a more realistic model of how breathing actually works. An example, but essentially the example that Bindi gave before is also asthma. So this is where you include some more biological detail as well. So you might inhale some sort of agonist, which leads to contraction, which leads to flow being diverted from those airways at the organ scale, and then that might feed back to what reaches the cells in the wall, and therefore how the cells respond, and you can get these interactions between scales as well. Another way the models have been used is to combine different imaging data sets on the same patients to get more information out of each data set individually. So for example, building models of the airway structure based on CT images, and then combining them with images of the lung function, so where the gas is going in the lung. This was used back in 2005 to identify airways responsible for poor patchy ventilation in asthma. Another example is combining CT with MRI data for a similar purpose, where you combine the function and the structural imaging to get a more complete picture of where the flow is going in the lung, and therefore how you expect airway resistance to change when you say, for example, apply an agonist or change the resistance of the airways in some way. And this is actually work by our first webinar speaker, Jessica Oakes, who will be speaking on March 21st. And you'll receive an advert for that and an invite shortly. Another example, and there are beautiful examples of thanks to Min Suk Kim for sending this video over, is where you use dual CT, so taking CT images at different times as the lung inflates and deflates to map out where the gas is going in the lung, and then they use that to simulate gas flow in and out of the lung, and then compare that to a xenon MRI imaging to show that it links up. And therefore, you only need one imaging technology in some applications. So finally, I just want to go back to the inert gas washout example that I mentioned earlier. So here's some work from the Robbins group in Oxford, where they've actually built a device for the accurate detection of various gases in the breath, and also an accurate measurement of the flow that someone is breathing in and out. And they've built that in tandem with a model which fits to the data coming out of that device, and essentially tries to account for some of those confounding factors I mentioned, and therefore give you more patient-specific measurements of the indices that are more accurate or more precisely what you're trying to find than the more generic indices. And we've shown in recent work that if you use similar techniques, then what you can do is you can actually predict the ventilation distribution in the lung that you would see in hyperpolarized gas imaging. So we can go from the multiple breath washout data, use a model to predict at least the broad properties of what you're going to see on the image. So hopefully I've convinced you that mathematical models of breathing have a rich history and we have a lot to build on here, and that there's plenty of opportunities being provided by new imaging, measurement, computing technologies. But the important questions for BioReam are what should our priorities be in terms of these modeling-based technologies in order for them to have the most impact, and how do we translate these technologies into clinical trials, and importantly into benefits for patients. So next up, we're going to have a talk a bit more about these clinical aspects, which will address these two questions slightly further. So thank you for listening.